Deep learning models stand for a new learning paradigm in artificial intelligence and machine learning. Recent breakthroughs resulting in image analysis and speech recognition have generated massive interest in this field, because also applications in many other domains providing big data seems possible. On the downside, the mathematical and computational methodology underlying deep learning models is very challenging, especially for interdisciplinary scientists. For this reason, we present in this paper an introductory review of deep learning approaches. The adjective deep in deep learning refers to use the multiple layers in the network. Early work showed that a linear perception can be universal classifier, but that a network with a non-polymer activity function with one hidden layer of unbounded width can. Deep learning is a modern variation which is concerned with an unbounded number of layers of bounded size, which permits practical application and optimized implementation, while retaining theoretical universality under mild conditions. Deep learning, the layers also permitted to be heterogeneous and to deviate widely from biologically informed contextual models for the sake of efficiency, tunability, and instability were the structured part.
Hello everyone, I will present the Open Macro model. Open Macro is a Java open source tool for building and evaluating probabilistic graphical models, such as Bayesian networks, inference diagram, and some factored macro models. In this section, we will demonstrate how to use Bayesian networks in Open Macro to answer the following question. For the COVID-19, whose prevalence is 3.4%, there exists a test with a sensitivity of 84.6% and a specificity of 91.8%. What are the predictive values of the test for that illness? Before doing so, I want to introduce the Bayes rule equation shown over there, and it can be proved by the following step as a background to know what the algorithm analyzes Bayesian networks. Now moving to the Open Macro part. First, we download an Open Macro and open it, and we choose network type as Bayesian network, shown here. Then we build connection between COVID-19 and the test. Then edit the COVID-19 node by entering the prevalence of 3.4% over there, and edit the test node. For the sensitivity of 84.6 here, and tapping the specificity of 91.8% over here. Then we run the result by click this button. So we get the result for the positive probability for the test is 0.1, and the negative probability for the test is 0.89.
This is Yami. Today I am here to discuss about sound classification using deep learning. One of the most commonly used applications of deep learning is sound classification. It involves learning to distinguish sounds and predict which group they belong to. Deep learning is the most recent application. Deep learning is a method of representing low-level data at a high level by stacking several levels using a non-linear module. This form of problem can be seen in a variety of situations, such as classifying music clips to evaluate their category. Low sampling frequencies have higher information loss but are easy and inexpensive to compute. Sound is defined as an audio signal with parameters such as frequency, bandwidth, decibel level, and so on. The amplitude and time of a standard audio signal can be expressed as a function of each other. Whether the description is Librosa is a great audio processing library written in Python. Few basic audio functions are also included, as in built-in modules. There are tools designed to assist you in capturing these sounds and converting them into a computer-readable format. Data exploration and visualization has been performed. The waveforms for different sounds like air conditioner, car horn, children playing, dog bark, or drilling, engine idling, gunshot, jackhammer, siren, street music has been recorded. The dataset has wide range of different audio properties and that need to be standardized before training a module. Most of the audio files has two channels. They are stereo and mono channels. Data pre-processing and data splitting. Librosa is a Python model for analyzing audio signals in general with a focus on music. It contains everything that needs to put together a music information retrieval system. The entire data set is divided into training and testing data set. Building data model and model refinement. We used a sequential model beginning with a basic model or architecture of 4 2D convolution layers and ending with a thick layer as our final output layer. The accuracy of the model on both training and testing datasets are reviewed. Here is the result, and adjusting the brand new deep learning program is the main properties of the dataset are total number of images, training set size, and adjusting the brand new deep learning program. It consists of convolution neural network, the main properties of the dataset, the advantages of the deep learning, the advantages of the sound classification using deep learning are organizing music collections based on their audio characteristics, music recommendations for radio channels, speech synthesis, and processing to create a synthetic voice for conversational agents. Hereby, I conclude that deep learning models such as the convolutional neural network have a large number of parameters which we can refer to as hyperparameters because they are not optimized in the model form. For distinguishing images of fruits and vegetables, we successfully built and training a deep learning model based on convolution neural network. The accuracy is improved well for using the test data as validation set and train the model. The deep learning model for sound classification was successfully registered using the train and test data sets. Thank you.
A convolutional neural network is a kind of artificial neural network that its weight-sharing network structure significantly reduces the complexity of the model and reduces the number of the weights. It is widely used in the industry. It has an input layer, a hidden layers, and an output layer. In any feed-forward neural network, any middle layers are called hidden because their input and outputs are masked by the activation function and final convolution. In a convolutional neural network, the hidden layer includes layers that perform convolutions. Typically, this includes a layer that performs a dot product of the convolution kernel with the layer's input matrix. So some applications of CNN, which is convolutional neural network, include artificial intelligence systems such as robots, virtual assistants, autonomous vehicles, among many others. So here is how usually a convolutional layer works. The filter size is usually a 3x3 matrix. It also determines the size of the receptive field. The filter is then applied to an area of the image, and the dot product is calculated between the input pixel and the filter. The dot product is then fed into an output array. Afterwards, the filter shifted by the stride, repeating the process until the kernel has swept across the entire image. The final output from the series of dot product from the input and filter is known as the filter map, activation map, or convolved filter. So as you can see in the image here, each output value in the filter map does not have to connect to each pixel value in the input image. It only needs to connect to the recipient field where the filter is being applied. The purpose of this project is to implement the custom CNN and ResNet CNN model on the fruit and vegetable dataset from Kaggle and increase the accuracy of the ResNet CNN model. The main properties of the dataset are listed here. The total number of images is 90,483. Training set size is 67,692, and test set size is 22,688 images. And there are 131 number of clauses, and each image size is 100 times 100 pixels. Well, to implement this project, we first need to go to the Kaggle kernels to download a API key to our computer and use the username and the API key it provided to us to get access to the datasets. And we choose the Google Colab here because it's a free GPU platform that we can use, and also it provides more times of GPU usage than other platforms. And then we will import noodles to prepare for our programs. Here we just need to load the directory path to the dataset and verify that the directories have the same number of clauses between the training and the test clauses. And the right side of exploring the data are the results. We're going to do some preparation before the training steps. So typically, it is common to split the dataset into three parts. Training set is to train the model, and validation set is used to evaluate the model while training, and the test set is used to compare different models or different type of modeling approaches and report the final accuracy of the model. And here we are going to do some transformation on both the training side and the validation set. I have only put the training transformation here. So what we are doing here is each image will be padded by 10 pixels and flip the image horizontally with a 50% probability, and then finally a random rotation of 20 degrees will be applied to the images. So here is the example of the training images, and this one is the original images in the evaluation steps by using these to show example codes. While datasets are loaded and transformed now, the next step is to define the data loaders to deal with the large amounts of data at once, because the system cannot process more than 67,000 of images once at a time. So we will set a reasonable batch size to allow us to process a certain number of data at each time without running out of memory. And here we are executing two different types of CNN architecture for both models. And while we are doing this, we got a warning here about the maximum number of workers in current system is 2, but the code was 3. Here was 3, and we changed it to 2, and this works well. The warnings has gone and the system still works good. And here is the example of the batches of images compared to the one that it only output one image at a time. It starts processing several images. So we are going to use the GPUs as the size of the model and datasets increases. We want to complete this program within a reasonable amount of time, and we choose the Google's Colabs. So here, to the get default device and to device will help a class device data loader to move the models and data to the GPU as required, and the device data loader is used to wrap the existing data loaders and move data to the selected device as the batches are accessed. After we have transferred in batches of data to a GPU, we will start defining the model. Before we defining the custom CNN model and ResNet CNN model separately, we first will have an overall clauses for both of them to evaluate. The accuracy function here is to work as a way to evaluate how well the model is performing, and a neutral way to do this would be to find the percentage of labels that were predicted correctly. For example, the accuracy of the predictions. And the image classification base will have the training step, validation epoch, and an epoch, and it will work as a trainer and will calculate the loss to both models. Now it's time to define the custom CNN model and the ResNet CNN model. ResNet refers to the residual neural network, and the picture here is the most important thing that would demonstrate the function of the ResNet CNN model. So for developers looking to quickly implement this and test it out, the most important modification to understand is skip connection identity mapping. This identity mapping does not have any parameters and is just there to add the output from the previous layer to the layer ahead. So the skip connection between layers add the output from previous layers to the output of stacked layers. This will result in the ability to train much deeper networks than what was previously possible. So here we use the ResNet 34 pre-trained model, but they also have ResNet 5, ResNet 50, ResNet 101, and ResNet 152 layers respectively, but we choose the ResNet 32. We use the pre-trained version. And here we start the training the models. Before we train the custom and ResNet model separately, we will define the whole function to apply to the both models. The first thing is evaluate function here. Will evaluate the training model every epoch. It will provide as output how well or how bad the training model is doing, and get learning rate, or will optimize the learning rate every epoch. And this fit one cycle function, which will perform the entire training process, will record the validation loss and metrics from each epoch and return a history of the training process. It would be useful to visualize the training process. And here we are able to change the maximum learning rate model, train loader, validation loaders in advance while training machine learning models. And these are called hyperparameters. While in the training phase, we will have the losses of training list and learning rate list, and we use the gradient clipping method here. It's a method where the arrow derivatives is changed or clip into a threshold during backwards propagation through the network, and using the clipped gradients to update the weights. After doing the training phase, we will have a validation phase. It will evaluate the training losses and learning rates of the program. Now it's time to training the custom CNN model and ResNet CNN model. Here I just list the ResNet CNN. It's just a matter of load them to the original model and afterwards move the model to the device, which is GPU we are using that previously selected here. But what the ResNet CNN model different from the custom CNN is we need to freeze these ResNet layers and train some epoch at first. And this only trains the final layer to start classifying the images. So we freeze it here and then train the final layer for a few epochs, and then we will unfreeze some of the layers and we will unfreeze the layers and train some more. The next step would be evaluating the models. So as we can see here, the learning rate for custom CNN model is super slow, as well as the ResNet CNN model, and the training losses is way more lower than ResNet's training losses. Validation losses is also way more less than ResNet CNN models validation losses, and compared between training losses and validation losses in custom CNN, we'll find validation losses is a little bit higher, and the validation accuracy would be at almost 100%, but the ResNet CNN model's accuracy is only 92.51 because it can process way more much more images than custom CNL and faster, but the accuracy will be lower. And here we try to modify the ResNet CNN model to increase the accuracy, which is higher than 92.51%. And what I did is we just add in another freeze layer and change the maximum learning rate in the last layer to a more smaller number, and I've got the result of 96.74% of accuracy. Now we are going to evaluate how the custom CNN model performs. As we can see here, the accuracy is going up and then drop down a little bit and still get close to 100%, and the training losses is more stable than the validation losses. It's close to 0 at the end of the 10th epoch, and the validation losses went up for once time and then it dropped down until close to 0. And the learning rate compared to batch number is more like a U-shape. It went up first and then dropped down. And this is the evaluation for ResNet CNN model. Not like the custom CNN model, the accuracy of ResNet is climbing for the first of fifth epoch, and then it keeps stable afterwards and close to 100%. And the training losses and validation losses almost keep the same. They are very close to 4.0 or even a little bit lower than 4.0, but the value is way more higher than the custom CNN model. And the learning rate here, as we can see, it also has a U-shape, but after 10,000 batches, it will like stable for a lot of time. So as a conclusion, we can find the custom model is managed to more like reducing the training and validation losses in comparison to the ResNet model. And the ResNet model is doing way more better on the timing management, and it can process way more images than custom CNN models. but with a little bit lower accuracy rate.
Hello everyone, my name is Jamil Ahmed and I would like to conclude the PPT by saying that while laying for open Markov, we have successfully demonstrated how to use open Markov to predict the values of the test for a given illness. In image classification, we have validation accuracy of 92.51% in recent model. To improve the accuracy, we tried changing the learning rate up and down, but the accuracy result did not improve and even decrease. When we added another freeze layer, the accuracy went up significantly from 92.51% to 96.74%. In sound classification, deep learning models such as convolution neural network include a lot of parameters, which we call hyperparameters because they are not tuned in a model form. Whereas for sound classification, we can see that the refined CNN model has got better testing accuracy, that is 87.63, and training accuracy scores 92.52. So we can conclude for the database that we had processed, the CNN model has a better chance of predicting the classification of a given audio sample over an MLP model. When testing data is used as a validation set and the model is trained, the accuracy improves significantly. Using the training and test data sets, the deep learning model for sound categorization was successfully registered. Thank you.